Hello, welcome back to SOH, the best office hours in the world, because you are part of it. So this is 2024, AP Physics 1, and this is problem number 4. And we see that there is a pendulum, and they give us 13 minutes, so it should be fast. However, this problem is indeed pretty misleading, the second question, and I'm not sure they thought about it, even though it's reviewed by college professors, but not me, and high school teachers. So yeah, you'll see. If you want to stay, there's something very interesting at the end of this problem. It's not wrong, but it's kind of, unrealistic, basically. And if you are a good student, and that's why you're here, then probably you would feel confused too. And if you try to do more, then you fail. Not good. That's not a good problem. Anyway, the first part is okay. So it says that, as always, let's go through the highlights. And if you want to stay longer for all those perks, then great. Otherwise, come back with another 5 and we move to the next one, okay? So a simple pendulum consists of a small sphere that hangs from a string with negligible mass. Always these strings will have no mass, don't worry about it. The top end of the string is fixed. Yes, fantastic. Otherwise, cannot swing. The sphere is pulled to point A so that the string makes an angle theta with the vertical. Okay? The sphere is then released from rest, so initially it's at speed 0, and swings through, okay, let's write it just in case, okay? And swings through its lowest point at point B. Yes, the work done, that's a little bit odd, right, to talk like that. By the work done on the sphere by Earth between points A and B is WE. Okay, so that's something important, but it's the work, okay? The pendulum is then taken to planet X. Well, okay, that would be cool. It's very expensive to do that, so anyway, but much more expensive than what we have to pay to take these tests. The mass of planet X is the same as the mass of Earth, so this is important. So let's write that. The mass of planet X is the same as the mass of planet Earth. But the radius of planet X is greater. Okay, well, so the radius, we assume that it's a circular planet, it's greater than the radius of Earth. The sphere, is again brought to point A, displays theta from the vertical, released from rest, and swings through. Okay, I mean, a silly thing here is that, well, if it has a very thick atmosphere or not, it would change, the motion of and the work on the pendulum. But let's see that we ignore, the effects of Earth. That's usual. So let's try to understand, what's the work here. The work is going to be the change of basically gravitational potential energy, and well, that's basically the work, because it's converted into kinetic energy. So the work here is mgh. So you just need to compute mgh in both planets. H is the same, m, the little mass of the sphere, is the same, so g. You have to derive how much is g. What is about the next question? A new pendulum. Oh yeah, but they say that the string is slightly elastic. So, and whether the period could be larger and also smaller. You have to remember the formula of the period, which is 2 pi square root of Lg, and then compute this in planet, on planet Y and planet Y, and then the reason why it could be larger and also smaller. Okay, that's something that we are going to do more in detail, but if you have it clear, then move on, come back with your 5, and then we will see the next one. But let's see. Justify why the work on the planet X is less than on Earth. So the work is basically mg delta H. That's the work done to move this small sphere from A to B, right? So the work on Earth and the work on the planet X depends on g. M is the same, right? Same. This doesn't change. Same. And this doesn't change. It's the same. Okay? They say the same angle. Same angle. So how much is g? G for a spherical planet, a spherical planet. So we assume that is going to be g. You may have seen this in class, but gm r squared. So the gravitational acceleration on planet X, since the radius is greater but the mass is the same, is going to be less, right, than the gravitational acceleration on E, because the denominator is greater, while the numerator is the same. So you have that. So in this case, then the work in planet X is less than the work in planet E, which is great. That says it's less. So thank you. And they help us. They don't tell us if whether it's less, more, or equal. So, well, thank you. Now let's go to the next problem. It says a new pendulum. okay, the same small sphere with negligible mass, all this is the same, but the string is slightly elastic. What does it mean? The length of the string may increase or decrease, but depending on the tension, but they don't provide a formula, right? They say that on Earth, where the sphere is again displaced theta from the vertical and released from rest, the new pendulum oscillates with period t. Okay, so we need to remember the formula of the period. Before was mg delta h for the work. So for a simple pendulum, you have this relationship where that's the length of the string and g is the gravitational acceleration that you have here. Okay. All right. So probably this is going to be in this planet y is going to be 2 pi, but what is going to change? The length in the planet y, right, and the gravity in planet y. While for Earth we will have the length on Earth and the gravity on Earth. So let's proceed as before. We remember that this is the gravitational force for a spherical planet. There's the acceleration for a spherical planet and on the surface. So in this case, what do we have? We have the radius is the same. So the radius of y is the same as the radius of Earth. But the mass is larger, the mass, okay. So you can see here that in this case, the gravity on y is going to be greater than on e. And this would tell us that, oh, then maybe the period on y is less than the period on e because we divide by a larger number, right? But the point is that we don't know how much is Ly. We have no idea. It could be more or less, depending on the tension, but no formula. There's no formula. So we don't know. So since we don't know how much is the quotient Ly divided by ay compared to, versus Le divided by G. So it could be, it depends. So if, let's think, so if Ly is less, so if Ly is less, then for sure the period is going to be less. So the period in y is going to be less. Now, if Ly is more, it depends. Because it depends if it can compensate the change of y. So at least we could say this. But the point is that there is no formula. We don't know how much it extends. So yeah, it could be both things. It depends on how long is the string. That's it. A plus. Now, this is misleading. And why is this misleading? You can, if you're done, you can leave. But why is this misleading? Well, we expect that they say that the new string is slightly elastic, so it's not terribly elastic. It's not going to going to be crazy. So we are close to the equilibrium point, right, of the string. In that case, we would expect that we have Hooke's law. Okay, so what we have is Hooke's law, and in that case, what do we expect? We expect that the force applied is directly proportional to the length that we have stretch the string. So we would expect that the force on the string is some constant by the increase of the length of the string. That's what we expect. Okay. Now let's think about the string. There is a weight here, mg, and that mg has is a stretching. How much is a stretching? Is this force here? So we have an angle here, theta. How much? Well, you can see that this force here is mg multiplied by the cosine of theta. Why is that? If you have it completely vertical, all the mg is stretching, and cosine of 0 is 1. If you have it like this, when theta is 90 degrees, right? Then none of it is stretching, 0. So cosine of 90 is 0. So what we have is that the force on the string, is k, to a good approximation because it's slightly elastic, k times the force of the string. Is mg cosine of theta, and this should be k times delta L, where this is the new stretch of the string. So in other words, the total length of the string should be L naught, like the rest length if we don't hang anything, without hanging anything, plus you can see here mg cosine of theta divided by k. That's the formula. Now for small angles, theta is approximately 0. We could do with the cosine, but for small angles, then the cosine of theta is approximately 1. The sine of theta is approximately theta, and the cosine of theta is approximately 1 minus theta squared divided by 2, but we neglect this term, so it's approximately 1. This means that we can simplify, and to a good approximation for small oscillations, for small angles, we have that the total length is the rest length plus mg divided by k. And that's very interesting, because when we compute the period now, the period is the following, right, of the small oscillations. Indeed, this formula only holds for small oscillations, so that's consistent with this. What we have is 2 pi, and then this is the new length, divided by g. So you have here a very interesting result. You have that indeed, this is constant. So even though it's going to stretch more if the gravity is larger than if the gravity is less, since it's going to be divided by g, there's a constant term. So indeed, the period in y, the period of the, you can say that is less than the period of Earth, because we have that this is a larger number while this is a constant. So great, that's what we, we have solved the problem, and indeed that's what it makes more sense. When would this not work? When would this save the AP problem? I'm impressed that they didn't think about it. But it would be if the Hooke's law does not hold. But we are close to equilibrium, and well, so if there is a non-linear relationship, I mean, they are not cooked, because indeed they are okay, they are saved, because they say that they don't give us the relationship. It could be more, it could be less, this kind of thing. But indeed, in any realistic situation, we would have a first approximation Hooke's law. So for small oscillations, we would have this. We would have that indeed we can predict that the period on the second planet is less than on Earth. Okay, so that's critical thinking, and they should have, improve the question or change it. The idea was to make people think that division depends on numerator and denominator. So if they both change and you don't know how one of them changes, you don't know how the fraction changes. That has a good intention. But if you will be, one of the students who is listening to our videos, then you would think about this, and then you would be completely confused, and that would be good if you're confused, because it means that you're good. Okay, so thank you, and let's go to the next one.